letting x and y be random variables, they can be anything, aren't given more information. Is it correct to say that the maximum of these two plus the minimum of these two are equal to x plus y? Then we're asked to assess, is it correct to say that the covariance of the max and min are equal to the covariance of x and y, since either the max is x or min, vice versa? So basically by symmetry, we're going to have to explain this. Okay, so let's start assessing the first question. The first question was, is it correct to say that the maximum of x, y plus the minimum of x and y the same as x plus y? Okay, that's a good question. So one way to think about this problem is to say the following, is that for some events, well, so think about what the random variable is that we're saying that for, x, when we write x, it's really just a function of some event of interest, say w. So w is an event that yields some numerical value, a. Okay, so we're running an experiment, we get w, and then we plug it through the random variable, and we get to observe the outcome, and then we assign a numerical value with some probability. So, and that experiment has a probability distribution. So if x, let's think about this. If x is equal, if x is larger, this numerical value now is larger than y, well, what would it mean? It would mean that, let's copy this and reason about this outcome. So if x now is larger, well, this has to be equal to x, right? And this event has to be equal to y. So here, I'm just going to write a question mark, and here indeed, we can say with an exclamation mark that x is equal to y. But does it also hold if we reverse the inequality? Let's check. Well, we can immediately see here with the same reasoning that this would now become y, and this now becomes x. And so we can indeed say that this inequality holds regardless of x being smaller or larger than y. Okay, so we can say that this first statement is correct indeed. Well, let's reason about the second statement, which said that, or claimed that, the covariance of max x and y, min x and y, is the same thing as the covariance of just the random variables x, y. All right, so this is what the claim was saying here, right? Okay, let's reason about this one now, and it's quite easy. Let me just say what would be wrong to say, because it was something I was running into myself indeed, which is that because we have the following reasoning we did here in this first statement, it seems logical that we can say we could just substitute x and y immediately here without really, it seems to be symmetrical, right? We could just say, this thing, let me just write on this side here in orange, we could say, well, the covariance, it could be, when x is larger than y, just as we reasoned here above, either this is equal to then covariance of x. So this has to be then x, and this has to be y. So, well, this thing should then hold, right? Because it doesn't really matter if you reverse the inequality or not. Right? Then it's the other way. It's y being larger, and so, you know, this then indeed equals covariance x and y. And I'll show you now in the following reasoning why this way of arguing is actually incorrect. And the essence of it is that this equality in here just happen to coincide. It's not that these terms are indeed equal to these things. It really depends on the sort of the experiment as such, just that the same thing after the experiment run, the max and the min and x and the y coincide. So it looks like they are similar, but it's just that they actually yield the same value, which is the different thing. Okay, and let's just unpack what this then means. Let's duplicate. I mean, another way. Let's just duplicate the max and the min here. So let's duplicate this. And duplication. Put this here. And I'm going to show you that this thing here to the left is, we have an expectation, and that's a different thing. Also from just running a just substituting the variables for each other. So we have the x and the y, that's just one random variable, then multiplied by the min of x and y. And this whole thing squared minus the expectation of max x, y times min x, y. So we have expectations here, and this will yield a constant. A constant. We'll just call this a. It gives you the covariance. It's just a number, right? It's not a random variable because we have taken the expectations over all the randomness that is in there. And you'll see here that this will be different from taking the covariance of x and y, which is the same thing. It's an expectation, x, y minus the expectation of x, expectation of y. And this will yield another constant. These things are basically, these expectations are not the same, and so hence the claim that that these equalities hold is incorrect. And actually it turns out that if you look at the covariance of max and min, if you plot these numbers, you can see that they do covary, because when this gives a high value, this other thing will sort of be capped by the lower value of y. So it creates this dependence between max and min, and so yeah, they are highly correlated, whereas x and y aren't.